metabolites like that.
That's good, that's good.
Okay.
Is everyone ready? Alright. So I'm Sia, and before I start, I would like to thank every one of you for being here today. I would also like to thank Mr. Geyser and the Young Dogs program for giving me the opportunity to engage in research and present it to you. So as you can see here, my research has been working towards metabolite identification in C. elegans. And if this doesn't make sense now, hopefully by the end of the presentation, it'll make a little bit more sense. So let's get started. So first I'll give you a brief outline for my presentation. I'll introduce myself, give you some background information regarding my research, and then take you through some of the research I did with my supervisors, and then come to some conclusions and answer any questions you might have. So a little bit about myself. My name is Sia. I go to North Oconee High School. I'm currently a junior at North Oconee High School. I'm a swimmer. I swim for my school team, and I also swim for a club based here in Athens. And in addition to this, I also participate in Science Olympiad, Beta Club, and Future Problem Solvers at school. So my site is CCRC, which stands for Complex Carbohydrate Research Center, and this is the facility where I work at. I work under Dr. Arthur Edison, who was unfortunately not able to make it today. My supervisors are Amanda and Bree, who are here today, and this is Amanda. She works primarily in genetics, and I work with her with the biosorter, which I'll be talking about in a few minutes. This is the biosorter right here. My other supervisor is Bree. She is a chemistry student, and I work with her with the mass spectrometer, which I'll also be talking about in my presentation. So the mission of our lab is to identify unknown metabolites using C. elegans, mass spec, and NMR. However, today I'll only be talking about C. elegans and mass spec. So what are metabolites? Metabolites are the things that we're trying to find here. And basically what they are is that they are the end product of our metabolism. And as many of you may know, our metabolism is a set of all the chemical reactions that occur in our body, and it's vital to our health, our growth, and our development. And as you can see here, metabolites are becoming increasingly important, and scientists are becoming more aware of the importance of metabolites in the field of metabolomics in human well-being. So just like genomics, epigenomics, and transcriptomics, as well as proteomics, all serve to be a big field in scientific research, metabolomics is also having this up-and-coming renaissance recently. So this is an overwhelming picture of all the metabolomic pathways that we know of. And right now you might be like, oh, this is too much, I can't process this. But if you think about it, this just goes to show how important our metabolism is, and how every single part of it connects to another, and how it's important into knowing more about our metabolism so that we can conquer related biological diseases. And so just to simplify this a little bit, this is just one single metabolomic pathway in which glucose is sent through the pathway to be used in the TCA cycle, which is then used for aerobic respiration to give human beings like us energy to go about our daily activities. So C. elegans is the organism that we use to identify these metabolites. And so what it is, it's a worm. It's invisible to the naked eye, so we have to use a microscope to see it. And it's a great model system to understand metabolomics in humans. So this is a picture of a C. elegans worm under a microscope. And this is just a brief visual of the C. elegans life cycle. And as you can see, it's fairly simple to understand. It hatches from an egg, and then it increases numerically as it goes through each life cycle stage. So the smaller worm would be like an L1 or L2 worm, which would stand for larval 1 or larval 2, whereas an adult worm would be an L4 worm, or a bigger one would be an L4 worm, and the next stage would be an adult. So this is another picture of a C. elegans, or of a C. elegans population, which I took under a microscope. And as you can see here, these bigger worms are more likely to be adult or L4 worms, whereas the smaller worms you can barely see in this area right here are more likely to be smaller baby worms, more likely L1 or L2 worms. So why do we use C. elegans? Well, first of all, it demonstrates similar metabolic functions to humans. So if we were to find a metabolite in C. elegans, we would know that we would most likely have it as well. So it also has a short life cycle, which makes it easier to do research on. It's transparent, which means we can see the internal organs of the C. elegans. It's self-fertilizing, which ensures that the C. elegans has the exact same genetic information as its parents. And then it's genetically diverse with over 500 different strains. So the research we can do on this organism is practically endless. In addition to this, it's also non-hazardous and inexpensive. So finally, what is mass spec? Mass spec is the machinery and the machine that we use to analyze the metabolites that we later extract out of these C. elegans. And basically what it does is it finds the mass and charge of molecules. And so I always like to use a certain analogy when discussing the mass spec and how it works. So I like to think of it this way. So what I do is I say, okay, I'm spraying a hose, and I'm spraying a hose at full power at a basketball, and I spray the hose at full power on a ping pong ball. Which ball is going to move farther away from the hose? The basketball or the ping pong ball? The ping pong ball. And that's because it has a smaller mass than the basketball. In a similar way, this mass spec machine works. So what it does is it ionizes all the particles, it accelerates them, and based on how far they accelerate, their mass and later their charge can be identified. So now that I gave you essential background information, I'd like to just make some connections for you. So the first thing that we do in our lab is we grow up a good population of worms. Most favorably, a population of worms that has the same number of worms in each life cycle stage. And after we create a good amount of worms, or a good population of worms, we put them through the biosorter. And what the biosorter does is it analyzes the amount of worms and the size of the worms. And after we generate enough data regarding our worm population, we put it through the mass spec, which is different from the mass spec I just showed you before. And after we analyze these metabolites in the mass spec, we generate our data, which tells us the mass and charge of these metabolites. And by looking at data, we can later hopefully identify unknown metabolites. So this is a video of the biosorter in action. And as you can see here, this right here is just a sample of different worm populations. And each one of these individual wells is a different sample. And so what it does, the biosorter sucks up each of these samples and each of these individual wells, and then shows us a graph that looks something like this. So this is what the biosorter shows us after it sucks up all the sample that we give it. And as we can see here, we can see there's a small population of worms. And not only is there a small population of worms, but there's also a lot of small worms. And we can see that because there is a large cluster of dots on the lower left-hand corner of the graph, whereas as we go up and to the right, it's more dispersed and there's not as many dots. So by looking at this, we can conclude that there are a lot of small worms in our population. And this is not ideal for our research because ideally we would want a population where there's the same number of worms in each life cycle stage. So you would see a cluster of dots that expand throughout this whole region and are equally dense in all regions. So to conquer this problem, what we do is we use GFP to stain the worms, because unfortunately the biosorter doesn't just analyze worms, it can also misinterpret worms to be, or misinterpret particles and other molecules to be worms. So to make sure that the biosorter is only counting worms, we make sure to stain these worms with GFP. So what GFP is green fluorescent protein, and this is what it looks like. And so what we do is we stain these worms, and we eventually want to reach populations that look something like this, where each life cycle stage has the same density and the same amount of worms throughout the life cycle stage. So what does this protein do and how does it aid our research? So what this does is it allows us to better be able to identify at what event and what time of flight we get an equal distribution of worms. And by doing this, if we are able to get an equal distribution of worms, we can accurately correspond different metabolomic functions in each life cycle stage to each other, and then come to even better conclusions. So after discussing this, I would just like to let you know my future goals as I continue my Young Dogs program. So one of my primary goals in continuing my research is analyzing C. elegans population growth and modeling it, which I'll be doing with another one of my supervisors, Gonzalo. In addition to this, the overall and the overarching goal of our research is to identify metabolites, and contribute to the ever-growing science of metabolomics. Because like I said before, metabolomics is starting to expand and starting to gain scientists' attention because scientists are seeing that it's becoming increasingly important in scientific research these days. And if we're able to identify these metabolites, we can kind of fit the pieces of the metabolism and the metabolomic puzzle together to later conquer related biological diseases and save lives. So thank you, and any questions?